I like to watch StatQuest. I really like to watch StatQuest. And I hope you like watching StatQuest too. Hooray! And now a word from our sponsor, Lightning.ai. Many of you people already know I work for Lightning.ai. I'm one of their lead AI educators, which is pretty cool. It's a pretty cool role to have. And if you don't already know, Lightning AI makes training neural networks super easy. So what I like about working for them is I like making hard things easy to understand, and Lightning makes hard things easy to do. So it's like a good combination. And in just a few weeks, I'm going to be releasing a video on how to code long short-term memory by hand and using the PyTorch function, and how we're going to use Lightning to train it and evaluate the training, and it's going to be super easy and super awesome. And I'm really looking forward to that. So that's a word from the sponsor. So without further ado, let's talk about cosine similarity. All right. So today we're going to talk about the cosine similarity. Wait, last time you said we were going to talk about CatBoost, not cosine similarity. Well, the cool thing is that the cosine similarity, which is used a lot in natural language processing, NLP, is also used in CatBoost. So, by learning about the cosine similarity, we get to learn about natural language processing and how CatBoost works. Double bam! Okay, so imagine we saw these sentences about the 1990 hit movie Troll 2. Oh, hold on. I see in the comments we've got someone from Brazil. Oi, Brazil. Anyways, sorry, I got distracted. Okay. So imagine we saw these sentences about the 1990 hit movie Troll 2. By eye, it's pretty easy to see that the first three sentences are similar to each other. They all express a positive feeling towards the movie. Like, we got I love Troll 2 and I like Troll 2, and I love Troll 2, I love it. Hooray! In contrast, the last sentence is from someone who does not like Troll 2, and they say, Troll 2 is bad. Wah wah. Party pooper. Anyways, so when we don't have many sentences, it's pretty easy to see which ones are similar to each other and which ones are different. However, what would we do if we collected all of the Twitter traffic for the last month? How do we determine similarities and differences in the tweets? In this case, we can no longer rely on doing things by eye, and instead have to get a computer to do it. This is where the cosine similarity comes in handy. The cosine similarity is a relatively easy to calculate metric that can tell us how similar or different things are. Bam! My voice is already going. What a disaster. I'm still new at doing these live streams, and what I need to do is put like a glass of water right in front of me or something like that. Okay, anyways. To get an understanding of how the cosine similarity works, let's start with a super simple example. Here we want to know how similar the phrase hello world is to hello. So the first thing we do is make a table for the words that appear in the phrases hello and world. In the first phrase, hello world, we see the word hello once. And we see the word world once. In contrast, in the second phrase, hello, we only see the word hello one time. And we don't see the word world at all. Now, given this table of counts for each word in each phrase, we can create a two-dimensional graph that has the number of times we saw the word hello on the x-axis and the number of times we saw the word world on the y-axis. Now, since the first phrase, hello world, had one occurrence of each word, we can plot a point for it in the center of the graph. In contrast, the point for the second phrase, hello, is on the x-axis at 1. And that's because we don't have the word world in it at all. Now, if we draw lines from the origin of the graph, which is at 0, 0, so where both world and hello are both 0. So if we draw lines from the origin of the graph to the points, we can see that there's a 45-degree angle between the two lines. And the cosine of 45 degrees, is 0.71. And thus, the cosine similarity between the phrases hello world and hello is the cosine of 45 degrees, which equals 0.71. Bam! That was not hard. Okay, note. Currently the second phrase is hello. But what if we're hello, hello, hello? But we still... whoops. I'm missing a slide here. Okay, when we have the phrase hello, 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 we've got hello 3 times. But we still have a 0 for the word world. So the only thing that's changed is we've got a lot more hello. In this case, the point on the graph representing hello, hello, hello would be further out on the x-axis at x equals 3. However, the angle between the two lines would still be 45 degrees. I don't know where the 0 came from. It would still be 45 degrees. And thus, the cosine similarity would be the exact same as what we got before, the cosine of 45 degrees, which equals 0.71. In other words, the cosine similarity is determined entirely by the angle between the lines, and not by the lengths of the lines. Small bam. Now, if both phrases are hello world, then they are exactly the same. And we end up plotting the dots that represent the phrases on top of each other, creating a kind of swampy green color. And the angle between the lines from the origin and the points would be 0 degrees. And the cosine similarity is the cosine of 0 degrees, which equals 1. So, when both phrases are exactly the same, the angle between them will be 0 degrees. And the cosine similarity is 1. In contrast, if the phrases don't have any words in common, like here, where the first phrase is hello and the second phrase is world, beep, then the angle between the two phrases will be 90 degrees. And the cosine similarity will be the cosine of 90 degrees, which equals 0. To summarize, when the two phrases have absolutely nothing in common, the cosine similarity is 0. And when the phrases are the exact same, the cosine similarity is 1. And when there is some overlap between the two phrases, but they are not exactly the same, the cosine similarity is a value between 0 and 1. Double bam! Now, the way we've been computing the cosine similarity, step 1, make a table of word counts. Step 2, plot the points. Step 3, figure out the angle. And step 4, calculate the cosine of the angle, is pretty tedious. The good news is that there is a relatively simple formula that can be computed super quickly on a computer to calculate the cosine similarity directly from the table of word counts. Dang, that equation looks complicated. Don't worry, Squatch. We'll go through it one step at a time. Thanks. These sigmas are shorthand for adding up a bunch of stuff. The I is short for index and is used to keep track of the word we're working on. I starts out set to 1, the first word in the table. In this case, the first word is hello. And N is the number of different words in the phrases. In this case, N equals 2 because we have 2 words, hello and world. A and B refer to the 2 phrases. In this case, let's let A be the first phrase, hello world, and B be the second phrase, hello. Now, when I equals 1, we plug in the word counts for the first word, hello. So we've got A times B, so that's 1 times 1, and then below, that's in the numerator. In the denominator, so in the bottom half of the fraction, we've got these square roots, these summations that are taking place in square roots, and we've got 1 for A, where we square the value, so we've got 1 squared, and we also have 1 for the B phrase, which is hello, so we've also got 1 squared there. Okay, so that's the first part in the summations that we're doing. And when I equals 2, we plug in the word counts for the second word, world. So again, we've got A times B in the numerator, so 1 times 0 because world doesn't occur in phrase B. And in the denominator, in those square root functions, we've got A squared, so which is 1 squared, and then we've got B squared, which is 0 squared. And when we do the math, we get 0.71, which is the same value we got when we took the cosine of 45 degrees. Bam! So we know that the cosine, this fancy looking equation for the cosine similarity, we know that it works. It's doing exactly what we thought it was going to do. Now, note, when we only have 2 different words in our table like we have here, then we can easily plot, I wrote plots, but I meant to write plot. We can easily plot the points on a 2-dimensional graph. Because we can put one word like hello on the x-axis, the first dimension, and the other word, world, on the y-axis, the second dimension. But when we have phrases with more than 2 different words, then we need more than 2 different dimensions to plot the points. For example, if we wanted to calculate the cosine similarity for these 2 points, where the first phrase, I love troll 2, is phrase A, and the second phrase, I love Jim Cotta, is phrase B, then the table will have 5 different words in it. And that means we would need a 5-dimensional graph to plot the points. And I have no idea how to draw a 5-dimensional graph. Wah, wah. The good news is that this is another way having the equation for the cosine similarity can come in handy. Rather than worry about how to draw a 5-dimensional graph, we just plug the numbers into the equation. Beep, 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 beep. And when we do the math, we get 0.58. So the cosine similarity between these 2 phrases, I love troll 2 and I love Jim Cotta, is 0.58. Triple bam! In summary, the cosine similarity is a relatively easy to calculate metric that can tell us how similar different things are. Note: if you haven't already seen it, Gymkata is an awesome 1985 movie about a gymnast who uses the parallel bars to defeat his enemies in Mortal Kombat. Bam! Alright, that is the end of our little presentation on cosine similarity. I can't believe it only took 15 minutes to get through it. I spent like a lot of time on it, but that's just the way these things go. And so now I'm just going to go over to the comment section and look through the comments. Someone says that they need this for their research, which is great. Someone says, I want to thank you for help with PCAT SNE and all topics. Didn't understand anything my professor said, but you made it make sense. Double bam, hooray. And we've got a whole hi from Chile. Hola, hola Chile, if you're still around. We got bam from India, bam. A bam from Iran, which is awesome. Greetings from Bulgaria. Someone just finished their PhD work and they thank me for the quest. That's amazing. I got some love from India. Hello, India. I got some good news for you guys in India. My book should be out this week. We're so close. I've had proofs printed. They look good. They just modified the cover to put an ISBN number on the back side. And as soon as I'm done with this, I'm going to look at that back cover and approve it. And then I think we've just got like 2 or 3 days where they test the system and make sure that the orders are going to be processed properly. And then I think the book is going to be out in India. So I think by the end of the week, for certain, it'll be, and it looks great and the quality's good. And get this, they're printing it in color this time. So I'm really excited. Anyways, what else do we got? Someone asked, what if there are more words? Does it increase dimension? And the answer is yes. The more you basically have a dimension for each word or different word we have in the phrases. Someone says it's cool to hear and see me say double bam. Love from Billy Billy, which is amazing. Holy smokes, I don't know how that works. So if you don't know, Billy Billy is basically the YouTube of China. YouTube is not allowed in China because it's a Google product, and all Google products are not allowed there, from what I understand. I've actually never been to China, so I don't know. This is what I've heard. So they have this thing called Billy Billy, and some of my videos are on there, and a lot of them are not. I would love to try to update. I actually have a Billy Billy account that I actually do not know how to update at all. I don't. So I have a friend that helps me, but they're super busy, and they only help me every now and then. So that's something I'd like to work on. Anyways, someone says, please do more on NLP, and that is the long-term plan. Someone says, what about the module and the size of the vectors? And I don't know what that means. That's João Lucas. Joshua McKay says, does this work with word embeddings? Presumably, yes. That's how, so, I believe that's, so I'm going to be honest of how I got to the cosine similarity. I got there in 2 different ways. One is through trying to teach CatBoost, which we will pick up on again next week, and we will use the cosine similarity. The other is I'm working on a video on transformers, which are used a lot, as transformers are a type of neural network that are used a lot in natural language processing, especially with automatic translation from one language, like a phrase that's in one language, to another language. And so I'm learning about transformers, and I'm learning about attention, and then I'm learning about word embeddings, and that means I learned about word to vec, which is, I guess, short to word to vector. And they use, once you do that, you can, once you have the embeddings, you can get a sense of how similar things are using the cosine similarity. So that is something. So here's the thing. So someone said, oh, Pam from Wales. That's pretty cool. Um, anyways, yeah, someone wants more about attention mechanism and transformers, and those are right around the corner. And by right around the corner, I'm talking on the I'm talking about on StatQuest timescale, which things right around the corner is usually like maybe if we're lucky, maybe a month, probably 2 from now, but that's pretty close for me. um, anyways, someone's really excited about me. Someone wants to know if there's a way to find jolly and happy if they're similar in natural language processing. So one of the ways that happens is instead of just looking at the individual words, we'll look at the entire. We'll look at we'll look at the entire phrase that the word is in. So if we see that happy and jolly tend to be in very similar phrases, i.e., the overall phrase has a very high cosine similarity, close to 1, then we can then guess that maybe happy and jolly are similar themselves, even though they're different words. So that's a way to do that. Bam! Attention is all you need. Someone said, which is a spoof on the paper that that first presented Transformers, which was, I think the title of that paper was "Attention is all you need." Um, so if you don't know, I have a video coming out on Monday on long short-term memory, which is sort of an early, before Transformers was a way to do natural language translation from one language to another. And what they discovered is that they wanted to focus. It was, there's certain words that are like super important in a phrase that really kind of determine the sentiment and the meaning. And so they created this thing called attention, which was a way to focus the neural network on specific words, and they could attach that to long short-term memory. But then they realized that if you just got rid of long-term short memory and you just were left with attention, things actually worked even better. So we're going to learn all about that pretty soon. So someone says, is cosine similarity better than dot product in higher dimensions? In theory, it is. Yes. So what? Well, that I don't know. I do know that in theory, it's better than the Euclidean distance. Because the distances all tend to end up being the same in really high dimensions. And the cosine similarity helps get around that. I believe that's correct. It's funny. I was reading, there were a lot of articles on cosine similarity versus dot product versus a Euclidean distance. And I was like, I'm not really interested in that right now. What I really want to do is just dive into the cosine similarity itself. So I didn't actually read up on a lot of the pros and cons of these different techniques. So I'm no expert, is I guess what I'm trying to tell you. However, what I will say is that the numerator of the cosine similarity is the dot product. And the dot product is affected by the lengths of those lines, and not just the angle. So the numerator is just the dot product. What we do is we add the denominator, and what that does is that scales the dot product to be technically between -1 and 1. But for language processing, where we saw that when things have nothing in common, the lowest value we get is 0, and when they have everything in common, the highest value is 1. So for language models, the cosine similarity typically runs from 0 to 1. Anyways, that's what the denominator does, is it scales the dot product to be within an easy to interpret range. And that makes it easy to compare different phrases that may have different vector lengths if we don't want to compute everything. And so that's kind of a useful thing. Someone asked if I can suggest a vector database. And the answer is no, I can't. Someone asked to please make some videos on recommender systems, and sure, I'd love to do that. Someone asks, I guess they had a question. Um, but they can't stick around to listen to the answers, so we'll just skip that, I guess. But I'll think about it. Someone asked about, when there's words that mean the same thing, or they mean different things, like the same word can be used in different contexts, and in different contexts it can mean different things. Um, uh, and they want to know how Google Translate can deal with that. And I think it has to do with attention mechanisms and the fact that attention can get the big picture of what the phrase is about, and then figure out what those words in the middle are all about. Someone asked if this is a PyTorch Lightning shirt, and the answer is yes. I love this shirt. This is probably my favorite shirt, by the way, because it makes me feel like I'm a superhero when I wear it. Do you play the piano too? Um, and the answer is a little bit. I play a little bit of piano. Someone asked, do we apply cosine similarity in text analysis? And the answer is yes. Yeah. I mean, that was what we talked about the first 15 minutes. Someone says, thanks a lot. And hooray. Someone asked if I can recommend some texts for mathematics related to deep learning. And the answer is no. I mean, the mathematics related to deep learning is basically multiplication and addition. I mean, there's a couple of twists on that. It's not that fancy. However, everybody swears that you need to know linear algebra, and I've actually found one case where it's useful to know linear algebra, and it has to do with the output of the long short-term memory PyTorch function. And I was like, oh, it would be nice to know linear algebra to understand what's going on here. In that it can take a single number and it can basically spread it out into more dimensions. And that's a linear algebra trick that, although it's just a function of multiplication and addition, is kind of a cool trick, and that'd be worth knowing about. However, can I think of a good book on linear algebra? And the answer is no, like resounding no. I've tried. I'm going to be honest. I've read like 4 books on linear algebra. I've tried to learn that stuff, and I learn it for about 10 minutes before I completely forget everything. Linear algebra is, like, some people just think it's the most useful thing ever, and it's kind of cool, but what I come away with is just enough to where I can look at matrix stuff and go, oh, that's just a bunch of addition and multiplication, and then I just write it out in longhand, and then I go, oh, I see what's going on now. So I'm not a huge fan of matrix algebra. I feel like matrix algebra is super useful for computers, right? Yeah, if you want to write an efficient program that does a lot of deep learning computations very quickly, you want to use matrix algebra or linear algebra to do that. That's awesome. But to actually learn about the concepts of what's going on, I'm not so convinced it's super helpful. What else we got? Maybe someone else, if someone else, by the way, has a favorite linear algebra textbook, put that in the comments, or not the comments, put that in the chat. Someone said that the sentiment about forgetting linear algebra is so relatable. Yeah, golly, I swear I've tried 4 different times, at least 4 times, and I know it. I know it for about 2 months, and then I forget all of it. It's just gone. Someone asked if I have more videos about PyTorch Lightning coming up, and the answer is yes. Hopefully in the next couple of weeks. I have one video coming out on the theory of long short-term memory coming out on Monday. It's already out for channel members and Patreon supporters who get early access to my stuff. So they can see it right now. But for everybody else, it'll be out a week from yesterday, which is not that long from now. And then I'm hoping like 2 weeks later, I'll have my long short-term memory in PyTorch plus Lightning. And I'm really excited about this. Because the lightning stuff is gonna it's gonna make it super easy. We can do, for example, we can do our training and we can generate all these really cool, super helpful graphs without having to do anything. You know, it's like sort of just built in. You just say, hey, draw these graphs. And you don't have to like be that specific. You can just say, there's this thing called TensorBoard. Excuse me, TensorBoard. You just say, let's use TensorBoard. And TensorBoard comes up in a web browser and it shows you all these awesome metrics about how well the training has gone. And then if you're like, well, it doesn't look like we're done training, you can use Lightning to pick up where you left off. You don't have to start over all the way from zero and like train again. You can say, oh, looks like we need more training, so we'll just pick up where we left off and train a little bit more. So we're going to show you how to do those things in Lightning, which are super easy and awesome, and I love them. So yeah, that's coming out in a couple of weeks. Can I recommend books for advanced learning of machine learning? And I always recommend my friend Sebastian Roshka's book on machine learning in PyTorch and scikit-learn in PyTorch. Hold on, I've got the book. I'll be back. This was written by my friend Sebastian Roshka. He's an awesome dude. And so machine learning with PyTorch and scikit-learn. I don't know if it's for advanced machine learning, but it's got everything in it. The book is a monster. It's like, how many pages? Almost 800 pages. It is a bruiser. Anyways, it's got everything in it, including like it does pretty advanced machine learning. It does convolutional stuff. Anyways, he also, by the way, he's got all kinds of cool stuff. He's got a cool newsletter. I'm just going to talk about how awesome this dude is for a little bit. He's got a cool newsletter. He's on Twitter. He's got cool stuff on Twitter. He's got this great blog that he's always adding awesome stuff from that I've learned from. Yeah, he's just a cool dude to know in the field and to follow and to keep track of what he's doing. Someone else suggests Deep Learning by Goodfellow et al. So that, I guess, comes recommended. So check that one out as well. I don't know that one. So someone says, let's see, let's move this. Do you have any idea in which situation, using which explainer it is it not relevant to log a high skewness feature during pre-processing? I don't fully understand that question, so we'll just move on. Which use cases in text analysis use cosine similarity extensively? I know it's used in the cases similar to market basket analysis. I think it's used to evaluate how similar phrases are, like from that are output from Word to VEC, and also used which basically boils down to any kind of word embedding thing. So I think that's helpful. I know someone says, "Wow, what a book!" Yeah, Sebastian writes a big book, but he's got a lot to say, so that's pretty cool. Anyways, I've powered through most of the questions that I can answer. If you have any others, feel free to post them. Otherwise, I'll get back to work on my next StatQuest, which is going to be long short-term memory in PyTorch plus Lightning, which I'm really excited about. So, how to calculate similarity between two matrices instead of a vector. I don't know. You could probably vectorize the matrices somehow. But I guess the assumption is both matrices are the same size, same dimensions. And if there are, you can just turn it into a vector and have the, and then just do the similarity on that. Do I think AI is getting easier? And the answer is yes, I do. Especially with Lightning. To be honest, it's like one of the reasons why I started working at Lightning is that they were like working really, really hard to make neural networks way easier to do. And so yeah, I do think they're getting easier. I mean, there's also a lot of auto ML, which is cool, where you don't actually have to tinker with the models yourself. You can just kind of get them all to run simultaneously and then pick the ones that you think are best. It still helps to know how to interpret the output of these things. Um, um, because otherwise you'll have no idea what the output is. So the theory, you still have to know things. So that part isn't getting easier. Um, unless well, you could say that because I keep making StatQuest videos on the topic, it's getting easier to learn the theory as well. So maybe that works as well. Steve recommends another machine learning book called Hands-on Machine Learning with Scikit-Learn, Keras TensorFlow, Concepts, Tools, and Techniques to Build Intelligent Systems by Giron, 3rd edition. So Steve is a wealth of information in terms of these books. Someone said, could I post the name of the book that I was holding some time back? Are you talking about this one? Machine Learning with PyTorch and Scikit-Learn. That's that. Someone recommends a good linear algebra book. That's good. And they're in Brazil, which is cool. They say good linear algebra book, so it's Arlindo Galavao. It says a good linear algebra book. I just butchered his name, by the way. Is Linear Algebra for Scientists and Engineers. So someone wants to know if you should say like you've got a lot of skew. How do you decide between scaling that feature or using the logarithm on that feature? It depends on the scaler. The logarithm, I mean, to be honest, I tend to think of the logarithm as like, that's my go-to when I see like a strong skew and it looks like it might be logarithmic. So that's my go-to. Scalars can be helpful for centering and sort of making things. A lot of people do what's called z-scaling. So you subtract the mean and divide by the standard deviation of all the features. How do you decide between using one or the other? When you don't know anything about the data and you refuse to graph it and look at it, I think maybe going with the scalar is probably the best thing. However, if you do know something about the data or you have the time to graph the data and you can see that it's logarithmic or you know that it's logarithmic, I think that's a much better way to transform the data, and it'll probably get better output and better results doing it that way. So it just sort of depends on how much time you have and what you know. Anyways, yeah, thanks for posting the name of that book, typing it in. I could type it out myself, but it would take like half an hour, especially because I know people are watching me type. And that would be a disaster. Typing with somebody watching you or watching me is I feel like it's like driving down the road with like the police right behind me. You're just like, totally stressed out. So that's that. So yeah, like I said, we'll do another live stream in 2 weeks, which I think will be interesting. I'll actually be in Barcelona in 2 weeks. But I'll do a live stream from my hotel room there. We'll just follow up on the CatBoost stuff. I think while I'm flying over on the airplane, I'll work on the live stream there. We're going to talk about how to build trees for CatBoost. So far, we've already talked about how to convert categorical features into numeric values using CatBoost method. We talked about that in the last live stream. Now we know how to use the cosine similarity, and that's part of how trees are built. And then it's like a step in how trees are built for CatBoost. And then, so the next live stream we do will be sort of like the details, the nitty gritty of building trees with CatBoost. And that's pretty much 99% of CatBoost right there. So I'm pretty excited because I've wanted to kind of cover CatBoost. And the idea, I don't know if you guys are aware of this, the idea for these live streams is kind of just like to motivate me to kind of get more content out there. And then once I got a bunch of stuff, I can assemble it into a single StatQuest. Like I could do a StatQuest on CatBoost, and I can do a StatQuest on cosine similarity and things like that. So this is my way of like getting material out there faster than I would have normally done it. It's a way of like motivating me. Someone asked, why don't I start my own newsletter? And that is something that I would like to do it one day. And I'll keep that in mind. That maybe I should do my own newsletter. That'd be cool. Especially when like, if I could talk about like, not just my own stuff, me, but also we could talk about sort of what my favorite resources are, whatever I just stumbled over, my favorite webpage for reading about something, whatever I'm learning about. I could say, hey, check out these resources. They're awesome. So someone says that they use linear regression for my sales statistics. Can I quit the linear regression for something better? I'm allowed to use only Excel. Well, that is a tricky situation to be in if you can only use Excel. I don't know. You can plot the data. I mean, you got options. Geez, but what are they? And I don't actually know. Can you do logistic regression in Excel? I don't know. I don't know. I do know that there's some templates out there for doing really complicated things in Excel, and you might want to muck around with those things. But my gut feeling is that if you're restricted to only using Excel, you're probably restricted to pretty much using linear regression. Anyways, yeah, sorry. I'm just reading the comments right now. So I think that's it. I think we're done for the day. Anyways, we'll do a little silly song. Bird alert. So thank you for watching my live stream. Thank you very much, and have a great day. And I hope to see you in 2 weeks' time when we finish talking about CatBoost. Hooray! Hooray! Thanks for everybody. I hope to see you soon in 2 weeks' time, and get excited about the long short-term memory video that's going to come out on Monday. Hooray!